All right, for the last part of this introduction to polynomial functions, we really want to try to integrate all of the things that we've addressed in this section all together and see how they all interrelate and ultimately be able to sketch out the graph of a polynomial function by finding as many characteristics as we can find as possible about it, just directly from its equation. Really, turns out to be pretty simple. Your text does have some information about, some things that you should be able to find, but I think for the most part, if we just kind of look at the equation, we should be able to kind of figure out a lot of stuff about it. So here we're asked to graph this function. It doesn't need to be like perfect, but you should be able to find a lot of characteristics to make it mostly accurate in terms of like finding particular points, like special ones, right? So what sort of special points might we want to try to find? Well, like x-intercepts and find y-intercepts, right? Find those sorts of things at least. Other things that should be key and of note is like when we're dealing with a polynomial function, you should probably be able to figure out what is its end behavior going to sort of look like, right? And then later we might look at some multiplicity aspects, minimum, maximum points, what may have you. But at least get some starting points, right? And we can kind of figure out what our plan is going to be from there once we find some key points and such, right? So I think one of the easiest things is to find is a y-intercept, because a y-intercept is always going to be a point where the x value is 0, right? So to find a y-intercept, you could just plug in 0, which then would be negative 0 to the 5th plus 18 times 0 to the 3rd minus 81 times 0, which is going to be 0. So you know that your y-intercept for this function right here is going to be at 0, 0. So voila, there's going to be 1 point on our graph, right? Pretty simple. Then we might want to try to find x-intercepts, which x-intercepts are always going to be real zeros, right? So then we'd have to plug in a 0 for y to find the x-intercepts, to find the real zeros, right? And then solve. So to figure that out, we're going to have to plug in 0 for y. And you get this equation right here. Okay, so we'll try to factor that right-hand side of the equation right there. Look for GCF first. You'll see that they all do have x's, but the first term doesn't have any number as a coefficient. The others have 18 and 81, so we'll just factor out variables. It's x to the 5th, x to the 3rd, and x. So you can take out x. And actually, let's take out negative x, right? Because the leading coefficient is negative. So if we factor out a negative x first from everything, then you get x to the 4th, this is going to be negative now, minus 18x, and x will be down by 1, so 2, and this become plus now, because we factor out negative, and then plus 81. Okay, and then we could try to keep going with this. So in the parentheses right there, to multiply to equal 81, but then add to negative 18, that's pretty simple, and just do negative 9 and negative 9, right? So we get negative x, and it'll be x squared for each bubble, right? So x squared minus 9, and x squared minus 9. But then each of those bubbles are differences of squares, right? X squared minus 9 would be like x squared minus 3 squared. So then you can break that to be x plus 3 times x minus 3, and then the other ones can also be x plus 3, x minus 3. Okay, so we get that. I'm just going to move this down a little bit so it's out of the way. Now, you could rewrite that as, because you got x plus 3 twice, you could write it as x plus 3 squared, and then also x minus 3 squared, right? So it should be pretty easy to find what the x-intercepts are then, right? So because you got that x factor, then you know that at 0, you're going to have an x-intercept, and then because you have the x plus 3 factor, you're going to get negative 3 to be the coordinate for an x-intercept, and then at positive 3, right? So those will be the only real zeros of the function, which will then be the x-intercepts. We already plotted where 0, 0 is, right? So it's of course going to both be an x-intercept and y-intercept. So now we can also plot these additional points. Now, one thing that you should also notice is that when we just found those zeros, that the 0 at negative 3 and then the 0 at positive 3 are going to be of even multiplicity because you have the squares on each of those. So we know that on polynomials that when there's even multiplicity, but it's going to bounce off of the x-intercept. So it's going to like either bounce this way or bounce this way at that x-intercept, and similarly for the other. So I think to figure out like which side it bounces off of, I think it would be helpful to figure out the end behavior of the polynomial function. So our end behavior for this polynomial function would be dictated just based on the leading term, which is going to be that term right there. We can see that we're dealing with a odd degree polynomial, so that's going to tell you that the ends are going to point in opposite ways, right? And then that leading coefficient right there of -1 is negative. So since they're going in different ways and it's negative, we would want the left end to be pointing up and then the right end to be pointing down, right? So generally, like over here it's going to go like this, and then over here it's going to go like this. Which then, if up here it's going up, then it's going to hit this x-intercept first, right, at some point. So at some point it's going to hit that, but then we know that at -3 it's got even multiplicity, so it's not going to cross through, it's going to bounce off, so it's going to go up like this, right, to whatever y value. So if you wanted to get a little bit more precision, like then maybe you should plug in -2 for x and find what y value it's at. So, yeah, but if I'm just kind of roughly sketching right now, it's going to have to come back down at some point, right, and then hit 0. But because 0 was a 0 of multiplicity 1, odd multiplicity, it's going to actually have to cross through, right? And then when it comes to this x-intercept, it's going to bounce off of it because it's even multiplicity and come back down and then look something like that, right? That's like good enough, right? We got a continuous graph, we got where the x-intercepts are, the y-intercepts, we got the end behavior, right? Now could we like try to figure out some more stuff about all of this stuff, like talking about evenness and oddness and maybe actually plugging in some points to get a little bit more accuracy? Yeah. But honestly, right, this is good enough. We have a general idea of kind of what the polynomial function is going to look like. Okay. So, just one more nice little example for us, and we should be good to go in terms of understanding the basics of what polynomial functions look like and characteristics of the graph, right? Okay, so we're asked to graph this function, and so I want to make sure we get an example where the function's given in a factored form, like this one is in, right? Just written strictly as a product. So you can pretty easily tell then that if it's in a factored form, where all the x-intercepts are going to be, right? So because you got this factor right here, then 4, 0 is going to be one of the x-intercepts. Okay, and then you got this factor right here, which is x squared plus 3. Now, if you have x squared plus 3, so like figure out what the x-intercepts would be, you have to set it equal to 0 and then solve. But then x squared would equal -3, so when you square root, x would be plus or minus I squared 3, which are not real. So that factor is not going to correspond to any x-intercepts, because you're not getting any real zeros out of that. So we don't really have to worry about graphing anything from that, right? From that last factor, you've got 2x minus 1 inside. So if you set 2x minus 1 equal to 0, then you'll just add 1 and divide by 2 and know that at positive 1/2, you're going to have a real 0. So then at 1/2 0, you're going to have an x-intercept. So only that point and that point then would be the only real zeros, and hence the only x-intercepts that this graph is going to have. So you'll have an x-intercept right there at 4, and then you also have an x-intercept right there at 1/2. Okay. Now, if you think about the multiplicities associated with those, right, this one was of multiplicity 1, because there's have an exponent of 1, and then this one right here is going to have multiplicity 3, because you got the exponent of 3 on that factor. Then for both of these x-intercepts, it's going to have to cross through the x-intercepts, because that multiplicity of 3 is odd, and that multiplicity of 1 is odd, right? So just keep that in mind when we graph this eventually. So then it might be nice to find like the y-intercept as well, right? So to get the y-intercept, you have to plug in a 0 for x, which would mean that the y-intercept would happen at what you get when you do this, right? Which will really just be 0.2 times -4 times 3 times the cube of -1. Which ends up being positive 2.4. So at 2.4, which is right about there, we know that the graph is going to have a y-intercept there. Yeah, outside of that, I think if you find just the end behavior of the function, you can get a pretty somewhat accurate sketch of the graph, at least. Um, so what we'll see here happening is that because this linear factor has an exponent of 1, and then you've got a quadratic factor there, that means that really you've got degree 2 factor there, and then you've got this linear factor that's raised to an exponent of 3, and then you've got basically kind of a cubic once you FOIL that part out. That overall, the degree of this polynomial, or the degree of g, is going to be 6. So you're dealing with a 6th degree polynomial here. So whenever you have a 6th degree, then you have an even degree, which means that the ends need to both be pointing the same way. So it's going to go up and up, or it's going to go down and down. And so then what dictates that is whether the leading coefficient is going to be positive or negative. So you'd like have to FOIL all this stuff out, but if you really think about it, like right there, once you cube it, you're going to get 8x to the third, and that's a positive x, and that's a positive x, and that's a positive number, is that then the term that will be having x to the sixth is going to have some positive number in front of it, right? So then we know it is going to like go up and up, right? So then since it's going up, it's going to have to hit this y-intercept, right? And then come down and hit this x-intercept. We already established that that x, or I guess this x-intercept right there, it's of odd multiplicity, so it's going to have to like cross through, so it'll come down, and then it's going to have to come back and hit this x-intercept and also cross through, right? And then it's going to have to come back up, and you know, it'll look something like that. So might there be some more like curviness that happens? Like maybe it goes like this and has a like minimum or whatever. Yeah, it's kind of hard to tell without like plugging in some more x values and just like making a table of values. But at least we've got a somewhat general shape of it. Okay, so we might be a little bit more off with this graph, right? Because there might be some more bumpiness and that sort of thing that happens in the inside of it. But at least we have somewhat of a general idea of some of the more important features of the graph, and that's really what we want to look to strive to get at least at this point in time.